Thank you very much, Martin, for the generous introduction, and thank you very much for coming. I think this is a Saturday, and seeing a full room on a Saturday is great for sure. And this is my first time in Sofia, which is great also. I'm going to switch the gears also a little bit after Otmar, talk about how we design machines today, and do a little bit of questioning of whether we're doing the right thing in designing our machines in terms of performance, energy efficiency, and sustainability, all aspects, and probably other aspects also. And I start, well, let's see, with this picture, asking how intelligent are our platforms? This is Mr. Bean riding his intelligent platform. If you get a bit flip in this platform, it will not look good. And I think that's true for self-driving cars today and many, many platforms that we have today. But let's get back to intelligence a little bit later. I think the major problem we're having today in our systems is our computing is bottlenecked by data, and important workloads are all very data intensive. If you look at machine learning, AI, genomics, all of these workloads that require rapid and efficient processing of large amounts of data, and data is increasing on top of this. We're generating much more data than we can process, and we want to do increasingly sophisticated things on the data as we go forward. And this is just an example from machine learning. This is a talk that was delivered by the chief architect of Cerebras. They're doing very interesting things, basically designing wafer-scale chips so that they can accelerate machine learning applications. And the reason they're doing it is they want to put computation and memory together as much as possible. And lots of compute power is needed, and lots of memory is needed also to train these large-scale language models, for example. And there's no end in sight at this point. We could, of course, question whether we're doing the right thing by doing these things, but before things get better, things will get probably worse in the sense that we will explore these models bigger and bigger and bigger and bigger, and maybe we'll find out there is a more efficient way of doing things. But that's not just machine learning. There are many traditional and forward-looking applications that are bottlenecked by data. These are some examples, and these references are to papers that analyze some of these workloads. And basically, we know that data is a huge performance energy bottleneck in these applications. If you look at the mobile end, we also have many, many applications that are constraining our systems, and data is a performance energy bottleneck in those applications also. I will briefly talk about genomics. This is an area we do a lot of work on, accelerating genome analysis. And this is where data is really exploding today. Clearly, with COVID-19 crisis, we had a lot of analysis of the RNA of COVID variants. And the reason we're able to do this sort of analysis today is because we have machines that can sequence genomes really well. And this picture over here shows that the cost of genome sequencing has been drastically reducing, especially with the introduction of new technologies for sequencing, and the cost of a transistor is not reducing as fast, which means that we're able to sequence many, many more genomes going into the future. The question is, can we really analyze them efficiently? And why is this interesting? Clearly, medical treatment and scientific discovery depends on it. We're good at building machines, but we're not very good at analyzing the data in between. I mean, by some definition, you could argue that we're good at it, but we're very slow at it. Can you, my definition of, are we good at this? Can you give a machine to you or to a doctor, and the doctor or you can sequence some genome and basically, based on that, make a decision relatively quickly, let's say within minutes, if it's a life-critical situation, right? We're not there yet because of the data bottlenecking our machines. And clearly, there are many applications of this. I'm not going to talk about this. Disease outbreaks and predicting them is one example. Developing personalized medicine is another example. Understanding what's going on everywhere is another example, and many, many other things. This is one data generator. So this is an example of data generator in genomics. You can actually buy this relatively cheaply and generate a lot of data, but it's terrible at analyzing data because it doesn't have computation capability in it. You have to move the data somewhere else, usually to a data center. So you're causing a lot of data movement, and we're going to talk about the energy of data movement to analyze the data. And I think this is a trend in our systems today. We're building extremely efficient data generators. This is in genomics. You can think of video as another example. You can think of internet as a huge data generator. And we want to analyze that data, do something on it. And to be able to do that, we move the data all around our systems at a macro scale across the entire world. And then we actually have a poor computer or a set of computers that are trying to analyze this data, and they're overwhelmed Basically, they're overwhelmed by data movement, as well as the lack of specialization that they have in the data. If you look at this part over here, the data generation is very, very specialized. Cameras are very good at generating the data, the type of data that they generate. Okay, so I'm not going to talk a lot more about genome analysis, but if you're interested, this is a fascinating area. There are papers that you can read about it, and even existing systems using FPGAs, you can accelerate a lot of these. But we're going to look into more into the future, not today. Maybe 10 years, 20 years down the future. If you're interested in going into genome analysis, we've written an invited article that summarizes a lot of things that are going on in the field today. Okay, so hopefully it's clear that data overwhelms our more modern machines. I'm going to give you a lot more data on this. Today, our machines are overwhelmed in terms of their storage and memory capability, communication capability, and computation capability, even though we designed them for computation. And there are a lot of other issues. Data greatly impacts robustness, energy, performance, cost, and security. Now, if you go back to the fundamentals, a computing system fundamentally needs three things: computation, communication, and storage. And if you look at how we have handled these over 80 years, let's say, we have heavily optimized the computing unit. We've kind of, in the grand scheme of things, ignored what's going on everywhere else. I'm going to show a picture that shows that. This is my cartoonish picture, which shows that computing elements, the red parts, cores, are a very small fraction of our entire node today, system today. Everything else is dedicated to moving and storing data. Even then, we're still bottlenecked by data and memory. This probably should ring a bell and have us ask questions. Are we really doing the right thing in the way we design our systems today? We're dedicating most of our resources for data storage and movement, yet we're still bottlenecked by data storage and movement. And if you don't believe me, these are real pictures. This is AMD's flagship processor. I circled, this box basically shows what fraction of the chip is dedicated to L3 and L2 caches. There's more caches. And they're adding more caches. This is IBM's flagship chip. This is Apple. I look at the processor, there's a lot of cache, and then there's memory, and then there's more memory, and then there's the darkness, which is storage. Clearly, there's a lot more over there going on. Except nothing is going on there except storage, right? We're not doing anything on the data in those units. Okay, so let me give you some data. We've studied these applications very intensively together with Google over the course of several years, and we found out that more than 60% of the entire system energy is spent on moving data across the memory hierarchy. We don't even go to storage in this particular case. If you go to storage, this goes up to 99% sometimes. And this is an average number. So my axiom going forward will be, if you want to design intelligent architectures that we want to rely on, and we do, I think, we want to handle data well. The question is, how do you want to handle data well? I'm going to talk especially about the first part. I'm going to briefly mention these two parts. But we want to ensure that data doesn't overwhelm the components as it is doing today. For this, we really need to revisit the entire stack. We need to look at intelligent algorithms, as Otmar mentioned earlier, intelligent architectures, as well as whole system designs, all the way from algorithms to devices, how we think about our devices. On top of this, I think we need to design our systems to be more intelligent. When we design our hardware and the software, we should enable them to make decisions on their own, as opposed to having humans dictate some of their decisions. Today, for example, when we design controllers, humans dictate decisions. As a result, the systems are very inflexible in the field. But if you use machine learning, for example, reinforcement learning principles in the design of some of these controllers, we can do much better. I'm not going to talk about that in detail. We don't have time. And the third thing is data has a lot of properties. We're clearly dealing with a lot of data. Data has privacy properties, security properties, approximability properties, error tolerance properties, performance properties, and many, many other things. Can we somehow take these properties and understand them in the system so that we can customize the way we build the systems for those properties? For example, when a memory controller treats data, it doesn't just say, oh, am I going to be a bit faster if I access this data earlier or later? Maybe it should say, is this data private? Maybe I should be more careful about how I'm accessing this data together with some other data so that I don't expose side channels in the system. Because we don't express those properties down into our systems today, because we cannot make such decisions today. I think going forward, we do need to. So basically, going forward, we do need to be more data-centric, data-driven, and data-aware. That's what those three things that I mentioned in the earlier slide meant. I'm going to talk about the data-centric portion. But if you're interested, we do have work on data-aware and data driven part. I think all of these require us to rethink how we're doing computing. I think this is a great time to be doing computing because we should be rethinking how we are doing everything, in my opinion. And we have a huge possibility. Hopefully, we will see that in a little bit. But I believe we can also get there step by step so that we can get the ideas adopted. We cannot change the entire stack overnight because this stack has been developed and has been present for 80 years, maybe longer. Okay, so let's jump into data-centric or memory-centric architectures, which I'm going to focus on. Even if you look at this, there are many, many properties that we want. We want to process data where it resides. I'm going to focus on that. But we want a lot lower latency and a lot lower energy data access so that we can solve some of the issues that were being discussed earlier, like energy and climate, potentially. We want low-cost data storage and processing and intelligent data management. I'm going to focus on the first one. The first one is interesting because this is not a new idea. We want to process data where it makes sense. So if you think about it today, where do we process data? We have to bring it from the source of the data, stored wherever it's stored or wherever it's sensed, all the way to computation units. That's a very small fraction of the system. Everywhere else cannot do anything to the data, as if it's some sort of taboo. And this is an example from the Apple M1 system, right? This is where we have to bring the data. It's a very small fraction of the system. But DRAM, storage, sensors over here, they do not process the data. So this is an old idea, actually. In the 1960s, forward-looking people thought about this. They said, basically, we should be merging memory and logic and processing data where it resides, let's say. And this is one seminal paper. If you know of an earlier paper, please let me know. It's another seminal paper. So what's new today? Well, why should we do it today? I think earlier talk kind of was a nice segue because we're having a lot of climate issues, right? We shouldn't be wasting a lot of energy. I think that's one answer. But there are other answers. Basically, we're kind of squeezed. We have nowhere to go, in my opinion. We are having huge problems with memory technology and storage technology today. It's not going well. We're having reliability issues, security issues, and those can be solved by more intelligence or computation inside memory. I'm going to very briefly focus on that. But I'm going to mainly focus on the systems on application side. Basically, systems and applications are demanding us to do something different because they're really bottlenecked by data, and we're wasting a lot of energy and power. And at the same time, we're at a point in humanity, I think, where we want to improve performance, energy, and sustainability all at the same time. We don't want a trade-off. We don't want to say, oh, we're gaining performance at the expense of sustainability or at the expense of energy. We really want to be improving all of them at the same time, in my opinion. So if you want to improve all of them at the same time, maybe we should be rethinking our systems. And so as a result, our designs today are squeezed in the middle. So before I go into a little bit more, I will tell you that if I was giving this talk 3 years ago, I wouldn't be showing some of the things I'm going to show in this picture. Basically, today, industry is moving toward this direction also. So industry is having 3D stacked architectures where you have a logic layer under memory layers, and this logic layer you can do computation. This is an example of it. Industry is experimenting with things. So this is introduced in 2019. This is a processing in memory chip. I'm going to mention that later in the talk. So today we're getting there slowly, let's say. And major vendors have been introducing processing in memory chips also. Samsung, SK Hynix, another Samsung, and Alibaba have been introducing accelerators, computation units inside the DRAM that can accelerate especially machine learning applications today. So we're going to briefly mention that later on. So the future is looking bright, basically. But and there are many other experimental chips and startups also. But I think before we go into that future, let's motivate this a little bit, because I don't want to go into technical details of exactly how this is done. You can read papers, you can watch lectures, etc. But this is motivated by memory scaling issues, partially. Memory scaling is a big problem. Memory is not doing well. So we've been testing memory a lot. We've been building a lot of infrastructure. This is one thing that we do in my research group. We build FPGA-based infrastructures so that we can understand what's going on in the memory system much better. And we've kind of perfected this infrastructure over years, let's say. But one of the things you find if you actually do these studies in memory is you can actually predictably induce errors in most DRAM memory chips. This is an example of a scaling problem. When you reduce the size of the cells, they become much more vulnerable. As a result, they become vulnerable to errors that you can predictably induce. This clearly should not happen because this causes a security problem called RowHammer. In fact, this is, as far as we know, the first hardware failure mechanism that can create a widespread, hardware reliability mechanism that can create a widespread system security vulnerability. And I like these articles that say, forget software, now hackers are exploiting physics. And I think that's a good explanation. I'm not going to give you any more detail on RowHammer, unfortunately. We don't have time. But there are papers on it, and there are tutorials on it. If you really want to know what's going on in 20 minutes, there's a 20-minute video on it also. But this is an example where we need intelligent computation and mechanisms and controllers to fix these problems in memory. And you say, OK, I don't care about DRAM. 10 years down the road, I'm talking about 10 years down the road, 20 years down the road, right? At that time, we're going to have a magic memory technology that's going to be good. That's not going to have these issues. Well, people have been trying. Unfortunately, it has not been as successful. In my opinion, there's no magic memory, so we need to look for there. But every memory technology eventually ends up requiring an intelligent memory controller. OK. So let's take a look at the systems and application trends. I think I mentioned this. I'm going to give you some data. I think the bigger picture is, in my opinion, do we want a future that looks like this, or do we want a future that looks like this? I would take the first one, I think. But I don't want to give up the performance that I get potentially from the second one. Meaning we want high performance, energy efficiency, and sustainability, and all at the same time. I don't want to trade off between them. So let's take a look at what is the problem that we have. Basically, today, we're moving data all around. As a result, we're causing great energy waste. This also causes a performance problem. To overcome the performance problem of data movement all around, we complicate our systems a lot. What do? We basically add a lot of mechanisms to tolerate the data movement latencies. We add multi-threading, both at the software and hardware levels. Multi-threading, out-of-order execution, heavy levels of redundancy, let's say, prefetching, many levels of caching. These complicate the system. And when they don't work, or when they don't somewhat work, they compound the energy waste. So we're in this vicious cycle in computing. We keep wasting energy over and over. And if you think about random access applications, this is even worse today. And many applications are going through random access phases today. So we're wasting a lot of energy. And the main reason is we're processing data far away from the data. And again, I showed this picture earlier, before. Today's computing systems are the cause of the problem, basically. All data is processed in the processor at great system cost. And let me give you a little bit of history also. We knew about this problem. This is kind of like, in my opinion, the climate problem, right? We knew about this problem, but we kind of ignore it until we're at the very end. Well, maybe there is no end if we keep ignoring it. So this is a quote from Dick Seitz, who was the chief architect of alpha processors in the 1990s. After they designed the flagship alpha processor, he basically wrote this one-page article saying, it's all about the memory. Stupid. They designed a core. They don't design memories. Basically, he said, we designed this processor. It's a flagship processor. It's able to finish 4 instructions every clock cycle. But on this important workload that we designed it for, it's finishing 1 instruction every 5 clock cycles. So it's operating at 5% of its efficiency. And he ends this article saying that, I expect that over the coming decade, memory subsystem design will be the only important design issue for microprocessors. I think going forward, we need to really make it the critical design issue. So this is data from my own PhD thesis, confirms the same thing. Most of the time, the processor is waiting for data. If you don't believe Dick Seitz or me, since everybody believes Google today, Google published results in 2015 showing that on their own data centers, most of the time, the processor is waiting for data to come back. This green part over here is showing that the processor is actually doing useful computation, 10 to 20% of the time, on their entire data center workload. And this is a beautiful paper if you want to read it from Google. That's performance. OK, performance may be OK. Energy is even worse. So this is data I borrowed from NVIDIA's chief scientist, Bill Daly, which shows essentially the energy of different operations that we do in our computing systems. This is a double precision floating point operation, 20 picojoules. It's a complicated operation, actually. A memory access, you could think simple, 16 nanojoules. That's 800x difference. So basically, a data access is much more energy hungry than computation. So the question is, does it really make sense to go to memory multiple times to get the operands so that you can compute something on the data and then write the result back to memory? Why not do everything inside the memory as opposed to putting things inside bringing data inside the memory, inside the processor chip? So that was a complicated operation. This is complicated. What about a simple operation? The energy disparity is even larger, 6400x. So if you want to do a simple addition, that's much cheaper in terms of energy compared to a memory access. I'm not even showing storage numbers. If I show you storage numbers, that's 2 orders of magnitude higher. OK. So as a result, if everything is in memory, most of the system energy is spent on data movement. OK, basically, I would argue that we do not want to move data. We want to change the paradigm, stop this processor-centric or compute-centric thinking, and enable computation with minimal data movement, compute where it makes sense, enable the ability to compute where it makes sense, where data resides or where data is produced, and essentially make computing architectures much more data-centric. And memory is one place to do it. Storage is another place. I'm going to give you some examples of this, but before we go into examples, let's cover the broad questions. So we want to be able to tell memory, which houses a huge amount of data, as you can see today. Machine learning is another example over here. Memory, can you do this operation? Can you do this function on me on the data? Can you search for this query and return me the results? And the memory does that and returns the results. Data doesn't move. Data is staying here. Memory, in parallel, searches inside itself. So this is easier said than done because there are many questions over here. How do we design the memory and the controllers? How do we design the processor and the communication units? Software and hardware interfaces to enable this. How do you design the software, system software compilers, languages, so that programmers don't go crazy while doing this? Because they will go crazy. Even programming compute-centric systems is not easy today. We're thinking about changing the paradigm, right? And how do you design the algorithms to fit what's going on in memory and theoretical foundations of computing as well? So it's clear this is an across-the-stack problem. I will mention the theoretical foundations over here because if you have studied algorithmic complexity theory, for example, everything is processor-centric. This processor-centric thinking is ingrained in our systems, essentially. You count operations to quantify the complexity of algorithms, right? You don't think about data. You don't think about how much data you're moving around. We should really be building a new theory of computing for data-centric systems. Okay, there's a lot I can talk about over here. I'm just going to give you some examples after this point, and then we're going to conclude. But if you're interested, we keep updating this article on arXiv that talks about essentially what I've been talking about, but a lot more as well. So we argue that we need to think differently from past approaches. I'm going to give you multiple approaches to processing in memory. There are two major approaches. One is processing near memory. The other is processing using memory. I'm going to mainly focus on processing near memory. Processing using memory is even more fancy. So what is processing near memory? Today, processor is here, memory is here. Why don't we move memory closer? Why don't we move processor closer to memory, such that computation units are inside the memory and they're coupled? Processing using memory is fundamentally different. Processor is here, memory here. Don't think about the processor. Here's memory. This memory is memory, right? But it also has capability to do computation. Every memory technology has some analog computation capability. Can we exploit that analog computation capability to actually do massively parallel computation? And we've been doing that also, but I'm not going to talk about using memory. It's a bit longer term. Near memory is already happening. So let's talk about near memory. So basically, we're very good at designing many accelerators in our system. All of them are compute-centric, meaning not close to memory. Why not put some accelerators on the memory side as well? And this could potentially be programmed similarly to a conventional accelerator. I'm going to give you, so here the question is what applications could benefit. We've been looking at graph analytics, machine learning, databases, and they all benefit. Let me give you graph analytics quickly. Graph analytics is everywhere. We do a lot of graph processing. This is an example application where you get a lot of random memory accesses and you have little amount of computation, so pushing things to the memory side makes a lot of sense. And one example technology that can enable this is 3D stacked memory and logic technologies. You have memory layers on top of a logic layer, and the logic layer can have processing mechanisms for graphs, for example, or general purpose. And other three-dimensional technologies are under development also. There's a lot of interesting work in that area. So this is a graph processing accelerator. I'm not going to go into the details of it, but it's essentially like a primitive GPU. Imagine a GPU 25 years ago, if you're that old. 25 years ago, GPUs were embedded in our systems. They were hidden. There were some enthusiasts who were trying to use the GPUs for something other than graphics. So we have this accelerator, graph processing accelerator, that's put into our system. It's basically a distributed system of interconnected memory plus logic cubes. There's interconnects in between. Inside one of these cubes, there's interconnects. Basically, we have processing mechanisms right underneath memory. And we don't move the data as much as possible. The programming methodology is really remote function calls, like distributed systems today. And the idea is not to move the data, move the function to the data. If you want to update some element in the graph, you move the function so that the processor that houses that graph node updates the graph. And there are some other mechanisms that I'm not going to talk about. So this system looks fundamentally different from, this is the traditional systems. There's processors, and there's memory, and they're separate. This system looks like this, processor and memory in one chip, and then you have a distributed system of those chips. As a result, processors get exposed to very high level amounts of bandwidth, as you can see. As a result, performance improves significantly. So when we initially designed the system in around 2013 or so, we get about 14x performance improvement. Later works, not ours, other people, improved it to over 100x. And there's no trade-off. Energy also reduces. When we initially did this work, energy reduction is about 8x. Later work showed that you could go higher than 100x. So basically, you're gaining 100x in performance, 100x in energy reduction, with all of the works compounded over the course of 7 years. Okay, and you can read more about it. Let me give you another example from storage this time. This is a more recent work. Here we want to be even more holistic, because in some applications, data is so large that even memory gets overwhelmed. You go to storage a lot. So we looked at genome sequence analysis, a particular application. So what do you do today? You move the genome, parts of a genome, from the storage system to computation units. Clearly, there's a lot of computation overhead because genome sequence analysis is not easy, and there's a lot of data movement overhead. Now, computation overhead, you can actually try to reduce as much as possible today with many, many heuristics, accelerators, filters, which we have been working on. But that makes the data movement overhead even worse, because as a fraction of the total execution time, data movement overhead dominates now. So why not do some operations on the storage system so that you move only a very little amount of data to whatever you have over here, including the main memory? And that's the idea over here. I'm not going to go into details because you need to figure out what to filter out. And if you do it the way we do it, you get rid of a lot of the data movement overhead, and you get significant speed-ups in close to real systems today. Basically, you can see the numbers are an order of magnitude at least, in terms of both performance and energy. There's no trade-off. You improve both performance and energy. Okay, there's more I'm not going to talk about. So let me give you what's happening in the real world relatively quickly also. These are research, and I can talk about research forever, but there's things happening in the real world, as I said. This is UpMem. UpMem has built these DRAM modules. They look like regular DRAM modules, but they're not, because they have processing power inside it. And this is a system that we have access to. And this is an example, basically. You have a memory bank. Next to memory bank, you have a general-purpose processor, multi-threaded. And if you're interested, you can read more about it. And we released benchmark suites related to it. In some particular applications, this outperforms CPUs and GPUs greatly, even though the processor is not perfect, and there are many design decisions in the system that are not perfect. This is just a first prototype, I would say. And you're welcome to contribute. This is actually, if you're interested in programming a data-centric system, this is a data-centric system that you can program today. And you can read the papers also if you're interested. We've been also looking at machine learning training on this processing in memory system. This is a tough workload, because this system is not designed for machine learning. It doesn't even have a native floating point implementation in hardware. It doesn't even have a multiplication operation that's more than 8 bits, because people cut corners to design the system, right, to begin with. And even then, if you actually play a lot of software tricks, you can gain significant speed up compared to existing CPUs and GPUs, and also energy improvements. Okay, so there's more. So clear, as I mentioned, that Samsung has been developing memory with machine learning acceleration, and they've been drawing pictures similar to what we have been drawing in the past, as you can see, 3D stacked memories. And they've been adding programmable computing unit inside their DRAM chips, and this is a real chip. It's not available yet as far as I know, but maybe you can talk to Samsung people. This is another module, not a chip, but module that was developed by Samsung and Meta. And the idea is to have lots of DRAM and a computation chip right next to a lot of DRAM so that you can accelerate deep learning recommendation systems. That's where they also feel a lot of data movement bottleneck. SK Hynix has developed another chip that is motivated by similar reasons, and it's an accelerator, and it's a more powerful accelerator, in my opinion. And Alibaba, clearly not a memory company, they've also developed their own DRAM chip to accelerate their recommendation systems. Okay, so clearly something is happening in the real world. Hopefully more will be happening. We will see. If you're interested, we cover a lot of this in our processing in memory course. As far as I know, this is the first processing in memory course that exists in the world. If you know something else, let me know so that we can collaborate with people. But we cover this in our courses a lot. Not just the real system, but a lot of state-of-the-art research. So as I said, I'm not going to talk about processing using memory. That's exploiting operational principles, analog operational principles of memory to do computation. I'll quickly say that this is not done yet, right? As far as I can think of, processing in memory is at a stage right now where GPUs were 20 years ago, maybe. And maybe that's arguable also. Hopefully, we will not wait 20 years. to get processing in memory everywhere, right? By the way, GPUs have enabled the machine learning revolution by enabling people to train things. The processing power that was enabled by GPUs really enabled machine learning to be mainstream today in 2012 and beyond. Who knows what processing in memory may enable in the future, right? So what are the barriers of adoption? There's a lot. So there's a lot that may not make this work. And a lot of it is software and systems, basically. Ease of programming, system and security support, runtime and compilation. I believe all can be solved with a lot of research and with a lot of mindset that's more data-centric. And clearly, we should not shy away from revisiting the stack. Okay, and hopefully, this will enable fundamentally energy-efficient architectures, and at the same time, fundamentally high-performance architectures. We won't have a trade-off between performance and energy. And for that, I think we need to rethink about how we do the data movement in our systems. So to conclude, I believe we must design systems to be balanced, high-performance, energy-efficient, all at the same time. That will lead us to truly intelligent systems. And I talked about the data-centric portion of what we're doing, but there's a data-driven and data-aware portion that I'm happy to talk about later. We would like to enable computation capability inside and close to memory, storage, sensors, everywhere where data is generated and aggregated. This can lead to orders of magnitude improvements. I've shown you some examples of this. This can enable new application and computing platforms, in my opinion. I haven't shown you examples of this, but genomics is a great example, in my opinion. I believe this can also enable a better understanding of nature, in addition to potentially being inspired by nature, as Luke mentioned in his talk earlier also. And who knows what else. I think the future is bright, but we need to do the hard work to get there. And a lot of people who enabled GPUs did a lot of hard work. That was not easy. I will mention this. So we have a lot of principles in the design of our computing systems, and we say we want to emulate the brain or something, but we're violating the basic principles of how this operates, as far as we know how it operates. There is no processor-centric portion of this, as far as we know. Compute and memory are distributed across the system. And I will thank people who funded us. Thank you, if you're here. And I will thank, more importantly, I will thank my research group who has done this research. And you can put some faces to who has done this research over here. You can read our newsletters. Everything I said is available online, so you can look at GitHub. So you can actually immediately improving the state of the art by looking at this, doing open source development. And if you're interested, you can also have a lot of information. We recently organized a special session on in-memory processing at a major conference. And our courses are all open online, as Martin mentioned. We have a lot of courses on many different topics in architecture. If you're interested, you can attend on YouTube. It's all live. You can even ask questions, actually. And I will stop here. Thank you, and I'm happy to take questions.